Hi guys, so today we're gonna talk about um another for Hey guys, today we're gonna talk about part C. So part C is similar to part B, but it's gonna be a little different because they're a reaction, the first order reaction with constant 10 moles that's happening. And another difference is that there's an N3 because there's a flux for N3 because earlier N3 is in a flux because it's in stagnant status, but in this case the component 3's hydrogen is a product that has a flux, so we can have to take into account to that, and then we can have to find um actual Y1 and Y2 and Y3 at the surface, like the mole fraction. So let's get ahead. So now I'm just gonna change this number, the diffusion coefficient for 1, 2, 1, 3, and 2, 3. So it's gonna be 230, and then this is gonna be, oh, actually this is 72. So it's 230. And then we're also going to change the value for pressure, temperature, and concentration. So our concentration is just pressure divided by temperature times the gas constant. So we're going to make equal P over divided by TE times R. And then so we have P and PA as 101, 300 Pascal. Temperature is going to be uh 548 Kelvin. And then so for N1, and then we should add an N3 too. And then we have Y1 and Y2. So at this point, we don't know what Y1 and Y2 are yet because over here, the 6C20 and 20 reaction are the original bulk gas composition, and we want to find their composition at the surface of the reaction. So we're just gonna make a reference, and then we don't include Y3 because um Y3 is equal to Y1 minus Y2. Oh, 1 minus Y1 minus Y2. So we're gonna do reference. Let's do this, give us 1 and 0. So these are our reference composition at the surface. And it doesn't matter what the value is, just stick to between 0 and 1. And so we know that N1 is equal to 1 is equal to um N1 is equal to, oh, I forgot the reaction rate over here. K is called KR, and it's gonna be 10 moles per meter square second. And so we have KR times, and one is KR times Y1. So you have 10, and then so you know that in stoichiometry, if this is without access, 1 mole of ethanol would produce 1 mole of acetaldehyde and hydrogen. And since they travel in different direction, ethanol is traveling down while acetaldehyde and hydrogen are traveling up. We're gonna we're gonna make N2 is equal to negative N1, so it's N3. So this is equal to negative N1, and then N3 is just N2. And also, I forgot that since the ethanol is going down, it's gonna have be a negative sign over here as well. Oopsie. All right. So now, for Y1, let's do the absolute value of N1 might divided by KR. Right? And then so now we can move on over here. And so since there's the presence of N3, we can have to fix our equation because earlier we didn't include N3 because N3 was equal to 0. So I'm gonna add, this is dy1, so we're gonna have y1 times and 3 plus, and then I'm gonna add another bracket over here, and then add the dollar sign. All right. And then same for dy2 dz. We can have y2, wait, let's add a bracket. Y2 times and 3 plus close bracket. Okay. 11 should be, yeah. All right, I'm not sure why it turned 0, but it doesn't really matter because we only use it as a reference. And then so over here, our goal is we want y1 and y2 to be 0.6, 0.2, and then I'm gonna take sums the difference square between this number, square, and then same for this. And then I'm gonna take the sum of these two number. All right. And then now I'm gonna use a solver to help us solve this equation, all right? Uh, let's see. Data, data solver. Let's use this, set this as our objective, and then changing variable over here. All right, and then make it minimum and then non-negative. Right, and then solve it. It's gonna take a little bit, a couple seconds. Perfect. So our solver gave us a result. So at about so we can answer this question. So at the rate reaction per area of catalyst, and then what is surface mole fraction of ethanol? So the surface mole fraction of ethanol is 0.0002269, and then you see over here it has like a ratio of 6 and 2, which is what we want over here. So 0.6, 0.2. So that's how we use the solver to approach this solution. Okay. And then vary the surface reaction rate constant to show and explain the exchange of diffusions and reaction limited operating conditions and its impact on surface versus bulk mole fractions of ethanol reactant. So I'm going to give you an example of the limited operation condition. So we see that a lot of manufacturers, a lot of companies, if they don't invest in a good machine that has a good rate reaction, then I can show you example. So if the rate reaction is 0.001, we can see that the flux is a very small number, which is a big limitation, but also when your reaction rate is high, like let's say 100, the reaction rate, the flux is still very low. So um that's why it's important to invest in a good that's why it's important to invest in a good machine. So you see that when the rea rate of reaction is small, the diffusion replenish the ethanol, and which slow down kinetically the reaction. But however, when the rate of reaction is high, this diffusion just depletes the ethanol into the surface, which makes the molar component, mole fraction at the surface similar to the bulk gas composition 622. Yeah, so which also slow down the flux, the reaction. So you just have to find the sweet spot in between, not too high of a rate reaction or not too slow to find to harvest the best outcome and have the best efficiency in product production. Thank you so much.